Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And now for the last speaker of the program, certainly not the least, especially for everybody in external research who works for him, so we'll, rah-rah. We'll ask him not to tell any jokes during this session. I think he excelled in that last evening, and perhaps later in the evening he'll regale us with some other. And did we change the microphone?
I'm going to put the microphone.
You're going to put the microphone on right now.
Powerful. Myself. Great. Okay. That's great. Okay. Let me just. Thanks very much. Thank you for the introduction, and thank you for all those references to my past, Jeffrey. Yes, it is. Yes. We did lots of interesting things with transputers and cosmic cubes and things. So. What I'd like to do today is I've enjoyed very much the conference and seeing all the enthusiasm and all the great talks that are now, I think, really making progress on some of the interesting problems. What I'm going to talk then is about what it really underlies most of the applications here, data intensive, but it isn't necessarily massive petabytes. As we saw from Jeremy Frey's talk, for example, it can be many files of small data files, and so it's the long tail as well as the big applications. So this is, if you like, a vision of the future. This is Microsoft's vision, but it is a fairly plausible one, I think. Seamless experiences, magic of software, power of the internet across a world of devices. So you've got, all of us now have MP3 players, PDAs, laptops, machines at home, and actually what we need to do is to make them all work together, to sync up, to communicate, and that's what the goal, I think, certainly of Microsoft, but also, I think, of this audience here. So, what are the big challenges? Well, we're now seeing the limits to Moore's law. We heard some of the implications of that from Jeffrey. We also see massive data sets or massive numbers of files or whatever, but data management problems, complex systems, and the fact that in order to do, for example, drug design, you need your biologists, talk to your chemists, talk to the geneticists. You need collaborative, multidisciplinary activity. And so it's really part of the world we live in. And we're also having a sea change in how we're going to be approaching these problems. Talked about massive data sets, federating them, integrating, collaboration, and it's one of my favorite quotations, more scientific data generated in the next 5 years in the history of humankind. I think that's undoubtedly true and will be true for a while. We're going to see Moore's law as we knew it ending, but we'll still see many-core, multi-core chips coming anywhere. Just the distinction between many-core and multi-core. Multi-core, I tend to believe, is sort of identical chips replicated, but you could imagine many-core where you have processing chips, then you have data, graphics chips, for example, all on the same chip. Processors, I should have said. And of course then the power of the cloud with your client, access anywhere, anytime, distributed loosely coupled applications across all types of devices. And that'll be the norm. So I think most of us would agree with that sort of vision. So Gordon Bell and I were looking with Alex Saleh at one of Jim's talks, and Jim likes to talk about the fourth paradigm, and data-intensive science is what I think the community is coming around to calling it. We do have this digital data deluge from all sorts of different sources. We have the problems of doing analysis and visualization. We have the legacy codes, the workflows, indexing, searching, graphics. And as Jeffrey pointed out, you're not going to get it all in your own memory. You're going to have to use the disks, and that's going to a sea change. And Alex Saleh talked about Grey Wolf, which is what Jim Gray used to call a data brick. It's actually a device with a much better balance for I/O for disks. And then at the end of the day, we'll need archiving, digital repositories which contain not just papers and text, but also videos, software, images, and so on. And libraries, what will a digital library, what does that mean, and how do we preserve things? Because we heard from the talk on the Keynote yesterday, no, it was this morning, about the problems of keeping CDs. Can you actually still play them in 10 years' time? And huge problems in preserving digital data. And so this is a slide from Jim. Experimental science, theoretical science, and it's clear in the last few decades for things like climate simulation, things like black holes, things like galaxy formation. Computational science is the only way to investigate some of these really compelling topics. So computational science is one of the methodologies now that's standard for doing scientific exploration. And I think Jim and I would like to pick out data-intensive science as a fourth paradigm because it requires a totally different set of skills than the other three. It's not to say that data-intensive science doesn't involve theory or computation. Of course it does, but it involves also knowing about how you do analysis, how you federate, how you data mine, how you visualize these huge amounts of data. So a different set of skills than the typical algorithms, numerical methods, and parallelism that we've done in computation. So I think we are genuinely seeing a new type of science where people can actually go and win the Nobel Prize by using other people's data, by putting it together with bits of their data, and you'll federate and do, if you like, these data scientific mashups. Just a word about my background. For those of you who don't know me, I used to be a particle physicist. That's where I first met Jeffrey. We used to write a paper every 10 years between us, and my first paper was, I think it was about meson structures, isn't it? I think so, in particle physics. And I then went back to Caltech in 1981 on sabbatical, and heard Carver Mead talk about the future of VLSI, where he predicted, he was the Gordon Moore Professor of Computation at Caltech, and he was the one who really understood why Moore's law works, and he predicted there were no engineering obstacles to making things faster and quicker, smaller and quicker for the next 20 years, and he was clearly right. But we are now reaching a different phase, and he spurred my interest in parallelism at that point, and that's why I became and did computing, and I also first met Richard Feynman, and I edited his notes on computation. But I did actually publish a book on gauge theories, I recommend. Okay, what I'd like to talk about is the open science agenda. What is that? Well, as part of my background, I ran for the equivalent to the UK equivalent of the NSF. I ran the UK eScience program from 2001 to 2005, and I've called it here eScience 1.0. And it was an interesting time to do it. It was, if you like, a precursor to what is now in the US, the Cyber Infrastructure Program. And in fact, we gave input, John Taylor, who was my boss, and I, to the Atkins Committee for their report on cyber infrastructure. But we're always in transition, but in 2001, certain things that were needed to do this distributed collaborative world were in transition. In particular, I would say authentication was just emerging with web services security and SAML and so on, and Shibboleth, of course. And then distributed computing was in a sea change to service-oriented architectures, so there were still people who pursued Corba, but service-oriented architectures and web services were emerging, but hadn't been fully defined. But if you wanted to do distributed computing reliably, service-oriented computing was actually a better way to do it, and I think I still believe that. there was, in the UK program, the particle physicists got the most of the money, and they wanted to do a particular type of distributed collaboration which emphasized computation. So they had a great emphasis on computation, and they really just wanted to compute on lots of data. They are a very smart community, and they don't have a problem of lining up on their clusters hundreds of thousands of lines of middleware. Before you can do anything, you have to make sure you have the right version of the operating system, you have to overlay all sorts of things. And they're smart enough to do that, and they made the grid, the EGEE, and in the US, TeraGrid and so on. They made it work with computer scientists and particle physicists and other smart scientists. But many of the scientific community, I'm talking about, randomly biologists, environmental scientists, whatever, they're not so much interested in the mechanisms of loading up large amounts of software. They just like to get started. And I think that was the lesson one of the lessons that I learned, that we didn't really focus enough on that type of user who really wants to collaborate and do various things more incrementally than having a huge amount of grid middleware. And it's also become clear over the last 5 years, I've attended more grid forum meetings than I care to remember, that there aren't going to be many of the grid standards that are produced by the grid forum that are supported and implemented by industry. And it's fine to have community standards, but we're not going to get large amounts of industrial backing and industrial strength software coming from industry in that space. So I think that's what one learned. And in 2004, towards the end of this period, Tim O'Reilly convened a workshop and put together what he badged as Web 2.0. And I won't go through all these in detail, but you can see there's Wikipedia, there's blogging, there's folksonomy and tagging, there's RSS feeds for syndication, mashups, of course. All these sort of things were just becoming. And what the web community has managed to do is, by using very simple protocols, which are supported by all the IT industries, it's enabled, even your grandmother can do a mashup, all right? And they can get started, they can start collaboration, social networks, and if they want more security, they can actually now go and get more security and so on. And so they can build something, they can get started at the collaboration right away without having to load up large amounts of software in a complicated way. And I think that is still necessary, but by far the majorities want to just get started. So I think the challenge that I see was well summarized by David DeRoe in a correspondence we had with Carol Goebel and others about what David called Research 2.0, and he made the point, decreasing cost of entry for digital research. It's all about data, and here are things like workflows, provenance, ontologies, and so on. It's collaborative, participatory, blogs, wikis, social networks, and all that sort of stuff. Community intelligence, I'm not totally sure I believe that one. Network effects. Open research, open systems and software tools. Researchers actually often happy to use just better ones rather than being perfect tools, and I think that's an interesting lesson too. And clearly tools that empower this bottom-up, so with the AI community going down ontologies, formally defined, but actually you can do quite a lot with this sort of community tagging, and so you can actually go and find things and do a different type of non-rigorous classification, which nonetheless is useful for the community. And a blurring of the lines between the digital and physical world, because we all have a part of the digital world with us. So if I were then to say what we would do now if we're doing the eScience program in the UK, and I think this is really the cyber infrastructure program, at least a part of it, using the web as a platform and things like the Web 2.0 technologies, because they're supported by industry, they're actually well funded, they're robust, they deliver, you can get blogs, wikis, all these sort of things. And I think the challenge for the computer science and the computational science and the e-scientists is to actually deliver powerful and easy-to-use tools and technologies to support the type of research that I've heard about these last couple of days. And what we need to try and do is to see if we can abstract, sets of tools that you can put together to make the research that the scientists want to do really easy. the moment I've seen some very exciting things, but I think it's sort of fragmented, and it would be good to see if we could abstract and get some generality which you can then specialize to different areas. And so the sort of things that I think are going to be important for this data-intensive research, interoperability and open standards, I think is clear. It's collaborative, it's multidisciplinary, so it has to have support for collaboration. Parallelism and multi-core are going to be a part of the space, and I'll give a couple of examples of that at the end. And of course, the client and the cloud, or software plus services, I think is going to play a big role. So I'll try and give you some examples of that as we go along. I thought I'd do a quote. I'm on the NSF Cyber Infrastructure Committee, and this is an extract from the minutes that I'm allowed to show. In order to help catalyze and facilitate the growth of advanced cyber infrastructure, a critical component is the adoption of open access policy for data, publications, and software, open access, open source, open data. And what I need your help is making sure Microsoft walks the talk that we do in our interoperability statement that Steve Ballmer made last February. Interoperability principles, open connections to Microsoft products, support for standards, data portability, open engagement with the open source community. So that's what I need your help to actually make sure we go and do just that. And so things like OpenXML, which gives you control of your Office files, I think is really an important component. The open specification of web services is another component, but that's what we need to do. So just as a couple of examples, we now have a plugin, a free plugin that you can download for the Creative Commons for the new Office suite, Office 2007. And so clearly we should all be using a Creative Commons license on the presentations that we give if we're going to let people share them. All right. So there's a plugin doing that. And here is another recent statement. Live ID is now an open ID provider. So I think Google, Microsoft, and others have all combined to make sure that the identification, the authentication works with the open ID community. And I think that's another good step towards open science. So what external research has been doing and exploring with many of you is how can we support the research life cycle. Microsoft typically has up to now targeted business and consumers, but it hasn't targeted the research community. Can we actually see if some of our products can actually be tailored, like Windows Workflow or SQL Server, so it actually becomes really useful to the scientific community? And obviously we recognize that we live in a mixed, heterogeneous environment. There'll be bits of Microsoft and bits of other types of players, and I've listed some of the other pieces along here. But if I characterize the research pipeline along here from data acquisition and modeling, collaboration and visualization, analysis and data mining, dissemination and sharing, the publishing and archiving and preservation. In principle, I think Microsoft have tools and technologies that can help with most of that thread. And of course, it's clear that some people want to use their own open source tools or maybe an Oracle database or whatever. And of course, that's what you should use. You should use whatever delivers the results for you. But what I would like your help is to try and see if we can get interesting solutions based on Microsoft technologies that give you a choice that you can use, and you really see that the technology can give you some value. So that's what we're trying to do, to see if we can come up with applications and technologies that can help you with all parts of the research process. And so, again, your help and suggestions will be much welcome. So this is some examples, and I invite you to think of other examples of things that you would like to enhance some of our tools and technologies. David Heckerman in the panel session yesterday talked about his Excel plugins, so we have some plugins for Excel. Here are some plugins for Word in Office, and this is a plugin here for the National Library of Medicine. They have a sort of schema. When you submit your paper to them, at the moment what they do is they send it out to be tagged up by a third-party company. But actually when you're authoring, if you have their schema that you can plug into your Word file, you can actually tag the document for the structure of the document as you write it, and the author is probably the best person to do that. So this is a plugin for the National Library of Medicine. This is another interesting project. again, with a plugin, which now tries to add the NLM schema adds largely structural information. But here, if you're writing in some fields, this is biology, this is with Phil Bourne and Lynn Fink at UCSD, with his Public Library of Science journal, and he also runs the Protein Data Bank jointly. What we're trying to do here is to make it so that when they're writing their paper, they know what their terms in the community, because they can plug in the particular ontology, because biologists like ontologies that are relevant to that particular paper, so they know the context, and then they can tag the words in their paper according to the words in the ontology. And again, that when you're doing searching, if you can search on semantic information, that will give you better than just keyword searches. So that's one of the efforts that we do. The authors don't need to be aware of the semantic technologies, but you can record the intention using the community's agreed vocabulary. And this is another one we're trying to do for the chemistry community, and working with Peter Murray-Rust and colleagues at Cambridge, trying to put semantic information into chemistry, so we can now do maths in Word, and Word now has, with the maths function, you can do something which looks pretty nearly as good as LaTeX. It's taken us about 20 years to do that, but we have now got it. And what would be nice to have is a way of doing chemical equations. And so here is a sort of schematic up here of some of the chemical equations. But you'd also like to recognize some semantic information. So when you see a thing like CH4, the computer knows that that C in that particular CH4 stands for a carbon atom, the H stands for hydrogen, and so on, and it understands something more about it. And so, again, that's a simple example of some semantic information. Peter can tell you much more. So, and there's another example, is what Jill Meziroff at the Broad Institute calls reproducible science. We've heard a lot about that today. You'd like to actually to be able to go and verify your results, and workflows are one way you can share workflows. Well, this is again using the Broad Institute at MIT. They have a system called Gene Pattern, and where the data is stored. And here, from within your document in Word, you can actually run the workflow and bring in the data. So this is an example of that, and you can then go out and run the workflow and update the data and so on as you're doing it. So that's, again, a plugin for Office. And the last example here is to do with data preservation. So as you're all aware, there was this big debate with ISO, and Sun and IBM were backing open document format, and Microsoft, which is a nice, simple, elegant format, but if you put your Word documents in that format, it won't look so good, because the reason the Word format's complicated is because it has a lot of richness. So in order to deal with the problem of all the existing Word files, what Microsoft has done is put Office OpenXML as an ISO standard. And in the next version of Office, you'll have a button, and you can either press your document to be Office OpenXML. It's all specified in XML, so it gives you the control. You can use OpenOffice if you want to go and manipulate it. You don't have to use any Microsoft stuff. And furthermore, you can have a button in Office, if you want to use it, which actually exports things in ODF. And so this project, the European Commission, with many national libraries, 5 national libraries, national archives, 4 universities, and so on, we were delivering converters from old versions of Word to the XML version. So then the XML version is yours. You can manipulate it exactly as you like. And besides the text all being in XML, all the metadata is all in XML, and it all goes round as one document. You don't have lots of different pieces of documents flying around. So we did converters from old versions to XML, and we also funded an open source project for a converter from ODF to OpenXML and back again. And that open source code is actually in Novell's OpenOffice suite. So I think you really have a choice here, and I think that's an example of Microsoft trying to be open and interoperable. And what we're hoping to produce with this consortium here is, if you like, a preservation toolkit that you can go and take all your electronic documents, put them into XML, which gives you some hope that you'll be able to do something with them some years down the line. Okay, cloud computing. So by the way, so if there are other things that you think we should be doing for plugins, for SQL, for Office, for whatever, please come and tell us. And let's see if we can do something together if there are other things that would really help your productivity and help the way you do your science. So this is what was announced at the PDC conference in Los Angeles last month. This is Microsoft's cloud platform, and in the latest edition of Wired, you'll see an article about Ray Ozzie, who is the chief architect of our cloud service vision. And so we have an Azure services platform here, and on this you have live services, SQL services, .NET services for developers, and you can have your application either running on your client or up in the cloud. All right, so this is the services platform, and you can do it with Visual Studio, our set of tools in .NET, but coming soon you will be able to do it in the other world over here and choose your development environment. So what I'll try and do is give you some examples of how you might use these in eScience applications. So the other thing that was announced are these Office web applications. So this provides much of the functionality of the standard Excel, PowerPoint, and Word up in your browser. And so it now gives you a really nice experience, and it's cross-browser. So yes, you can use Internet Explorer, but you can also use Firefox or Safari and probably Chrome in the future. Synchronization between desktop and browser, it actually really is a nice experience, and it fully integrates with your Office on the desktop, but also in the cloud. And so this is, at the moment, a community technology preview, but it will be coming out in the next release of Office. Why do we care about this? I'll just use this as an example. You've all heard of Flickr, which is sort of my example of the paradigm of a cloud service. My family's scattered around the world, and to keep in touch, we load our photographs into Flickr, which we can either keep private to our family or we can release it to the world. And I'm told that several thousand people have followed me falling in the Congo-Cut River in the Arctic National Wildlife Refuge, which you can see up on Flickr. So that's an example of a cloud service. You can access it wherever. You don't care where it's stored. You can just get it. So that's what I think distinguishes a cloud from a grid, actually. This is another example which I think is interesting, and I think what it offers a service like Flickr for storing your photographs. It claims to have, 370 million photos and 300,000 users. But it also has an interesting claim here. It claims a profitable debt-free company. So they haven't got huge amounts of venture capital which they're trying to pay off. And the reason is they don't have any equipment. They don't have any machines to host this on. It's all hosted in Amazon's cloud. And so what this gives you, the cloud services, will give you the opportunity for your smart undergraduates, grad students, and faculty to go and start companies organically and grow the company as the business grows. And so I think it's really a challenge for your more entrepreneurial and innovation. I think you can do lots of interesting things with the cloud. And Microsoft's ambition to make our tools and services in the cloud, so it's easier for you to do that than with other people's. But, time will tell. So that's why I think it's of interest that you can do things with the cloud that you couldn't dream of doing otherwise. I mean, you can do a class. Berkeley are doing a class where they actually have, students programming on hundreds of servers. Well, that's because they're renting these from Amazon. And again, you can do new things with cloud services. So what about client and cloud services for science? So let me just give you 4 examples. Virtual research environments, an oceanography workbench, private clouds for personal health, and then finally a short video I will show. So this is one of the projects we're doing with the British Library. It's based on SharePoint, and it's trying to introduce ways of giving an environment for looking for content management, for social networking, for blogs and wikis, RSS feeds. All you can tailor into your own space, your own search databases that you want to put there, your search engines, whatever. So it's currently being evaluated by the British Library and a number of sites. And it's an interesting thing. But you have to run it, you'd have to run SharePoint. And SharePoint's a complicated thing. I only know 2 groups, research groups, who run SharePoint in the actual group, and they're both here, Jim Davis and Ian Buchan, who have SharePoint experience and have a SharePoint administrator and all that sort of stuff. But in the future, you'll be able to run SharePoint in the cloud, and you won't need to have all the expertise to update, to manage the software, and so on. And so you'll be able to have your environment in the cloud. You'll have some of it locally. You may keep some of the data locally, but you might put some of the data in the cloud. Interestingly enough, from our beta evaluation, the one thing that the researchers are worried about are letting go their data to the cloud. So I think you need to recognize that's what users are going to do. They're not going to want to let their data be purely in the cloud. So I think that will come. Roger and his team, Roger Barget, talked about the Trident Workflow, scientific workflow, again using this ocean observatory project. And again, this is interesting. It uses a range of technologies from Windows Workflow, high-performance computing, SQL Server. But what you can do, and what he demonstrated at PDC with his team, that you can either store the data locally on your machine, or you can store it in the cloud using SQL services up in the cloud. So again, it'll give you a whole new range of options. So those are for scientific collaborations. Future of health. It's a very interesting field because health is actually affecting not only the developed nations but also the developing nations, huge health problems. But in the Western world, we're going to see personal monitoring, smart medication, personal health management, data. I don't know how many of you are participating in 23andMe. It's when you spit into a tube and send it off, and they analyze your SNPs in your DNA, so you can find out what horrible diseases you're not going to get, or whatever. Bill Gates was asked why he didn't want to do that, and he said, I don't want to know what I'm not worried about now. Why should I want to know what I'm not worried about now? Right? Because you can't do anything with the data except have a sort of community site. But I think it will become more interesting, and I think you will see the $1,000 genome, the X Prize, claimed in the next few years. So I think it's a very interesting area. And of course, what you will have then in your cloud, Microsoft has a thing called Health Vault, which is intended really for not only for hospitals, but also for personal users. You might put all your medical records there, and so whenever you're around, whenever you are in the world, you have all your medical records. So this private cloud contains the context and can be used to give you information. You can have RSS feeds and so on, which are relevant to your health records. And so Health Vault is a section of services to collect, store, and share health information. The user controls that and decides who they share it with. They don't have to share it at all, and you can search it, and you can set the system to search for relevant health information and so on. So that's an example, I think, of a smart private cloud. And the last example I'd like to give you is this one. So let me just explain it, and then I'll show you a brief video. But it's an interesting example for the following reason. So what it is, it's a robotic receptionist. So this is, imagine you're in Microsoft, this is the receptionist, and she's booking you a shuttle to go to the next building, or the building at the side of the campus. Okay, so a lot of things are going on. So up here are 8 cores, and you can see the processing in the 8 cores. What's going on, how much computing is being done. Avatar is here. You have to generate the face and the voice and the lip movements. The lower left of the screen is what the user sees. What we're trying to do here on the main screen is visualize and actually figure out who's speaking. So these are array microphones here. And you'll see a little red dot here. It shows you where this person's looking. And this red dot will go from this person to this person, depending on how they're speaking. Okay? Mimics Fusion Sight. These are the microphones. Mimics spatial hearing, so you can see that this will go over here when he's talking and go over here when he's talking. And it's context sensitive. So here, this is 2 typically scruffy Microsoft researchers. This is Eric Horvitz, in case you didn't know. And then you'll see someone coming in, looking a little more formal, and she clearly decides that person's a visitor and needs to be treated differently and isn't part of these two, all right? So, again, it also tries to notice when there's something going on that their attention strays, it brings them back into the conversation. But the point I want to make in here is that there's lots of things going on, huge amounts of processing, right? It's loosely coupled, it needs the power then of multi-many core, and you can't send the data up into the cloud. It's coming in all the time. You're generating speech synthesis, all this sort of voice recognition, all this sort of stuff. You're not going to have time to stream it up to the cloud and then do the analysis and stream it down. So this is absolutely an example which you're going to require local processing, local data storage actually on the machine. So let me try and run the demo, and you'll see what happens.
Is we have more headcount coming onto the project.
That's great. That's great. On the Digital Interaction project?
On your project, on
That's
your
great.
team.
That's fantastic.
Hi. My name is Laura, and today I'm here to help the receptionist with shuttle reservations. What's your name?
I'm Dan, and this is Eric.
Nice to meet you. Do you need a shuttle?
Yes.
Which building are you going to?
I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for building 9 for 2 people. Over.
So,
Are you visiting someone?
Okay.
Yes.
So I think
I'll
everything should
help
be
you
all set.
register in just a moment.
fabulous.
Okay.
I think we're set.
Okay.
Excuse me, sir.
Yes?
You will be on shuttle 53. It should be here any second.
All right, thank you.
Bye-bye.
Bye.
Hi.
Hi. My name is Laura, and today I'm here to help the receptionist with shuttle reservations. What's your name?
Jichen.
Nice to meet you.
Okay. So it's clearly rather primitive, but the point I wanted to make, it is the sort of application that you're going to need lots of processing locally. And so I'm waiting for the next time I come to one of these conferences. I want to have one of these so it can actually recognize as facial recognition, and it can see that, oh, it's Jeff, but he's looking a little older and his hair's a bit grayer, but it is Jeff. Oh, and last time you met him was 2 years ago, and you talked about this, and he owes you a beer, all right? So, and of course, Jeff will have one of these too, and it says, I think it's Tony Hay, and so on. So that's the sort of devices I want to see. Anyway, I thought you'd like to see that demo. I think it's quite educational that although I think a lot of things will happen in the cloud, you will need applications, and there will be interesting applications made possible by the power of multi-core actually in your hands. So the future, right? So a world where all the data is linked, data and information is interconnected through machine interpretable information. There's so much data, you're not going to be able to look at every image and so on, inspect it manually. You're going to need computer assistance. And for that, you need to put some semantic information with the data so you can actually go and find things that are relevant, and the computer can find it without you intervening. So here's a simple example of an RDF type triple. Paper X is about star Y. And so you'll actually know something about, it's not just any website, it's a site containing sequence data, this contains protein structure data and so on. You'll know information rather than just the HTTP address, or here again you have subject, predicate, object here. So social networks are, if you like, a special case of these data meshes, as we call them. And again, it's all very simple, well-known formats are going to enable that fairly quickly. And so, in the end, you'll have something like this, I believe, and I think this is a fairly credible. The amount of stuff you have on your client or in the cloud can depend, it can vary. It can vary for you, it can vary for different people, it can vary for you for different times, for different jobs. But you'll have all sorts of services, instant messaging, identity, blogs, networking, storage and data services. This is our Azure services, but there will be others there, and you'll have ID management as well, somewhere up here, identity management and so on. And over here you'll have the things that you find most useful that you don't want to have necessarily in the cloud, and you'll keep on your desktop or on your laptop. And so that's the vision of the future, I think, that we're all going towards. And really what I would like to do is to see if we can make tools and technologies that are better suited to help scientists do that. So I ask for your help. Thank you very much for listening. Sorry.
And we do have time for questions. And again, microphones, please, for capturing process. And someone must have a question.
Peter. Peter always has a question.
So having been part of the eScience 1.0, one of the things there perhaps was that...
Did you agree with my characterization of it?
Yes, and I did during the process as well. One of the things there was that was heavily designed, and a lot of it didn't work out. Whereas what we're seeing now is that a lot of things are done very much on an evolutionary basis. A lot of things are tried. Many of them don't work, and so on. So to what extent do you think we design the future, and to what extent do you think we simply try lots of things out and see what works?
Well, actually, I think the academic community has a major role to play in this. And I think Microsoft has now a much more open attitude towards open source. So what I think the academic community can do, it can explore a much larger space of possibilities than any major company can, because a major company has to limit its risks. So whilst it is true in SourceForge they have 150,000, whatever it is, of which 95% or more have only 2 users and 2 developers, and they're the same people, all right? So, you know, people say, well, it's open source, you can have my software. But actually, the biologists just want software that works. They don't want to be, well, it doesn't work, you can fix it because you've got the source. Well, I remember a colleague in Southampton telling the librarians, oh, you can easily tailor it, just write a few lines of Perl. That's not typically what a librarian does. So, so I actually think that by exploring lots of different areas, you will find ones that do work, and there will be areas parts of the space that the academic community can explore that will not be possible for companies because it's too expensive. They have to minimize the risks. They put huge amounts of effort in this, and it doesn't work. But then it's really very costly. But I think that, so what open source, I think, at its best gives you is failure for free, all right? Because actually you can then say, oh, this one guy had the right idea, brilliant idea, and everybody then can go and coalesce and build a community around it. So that's why I actually quite like the Web 2.0 analogy, that enables people just to get started and build things on it. And I think that's what we should have done a little bit more, but we did need to have something to coalesce around. It was just the time we did it, that was what we coalesced around, and that's what the particle physics wanted to do. So it was an interesting transition time. But I think it's really, you know, this community can go and change the world. And cloud services make it easier for you to do that.
Other questions? Thank you.
So actually I have a question about that. Have you explored through the science community, how much are they expecting about the cloud computing? Because I think, you know, science communities are kind of like cowboys, right? They want to do their own thing. So,
well, okay. I think the explorations in scientific applications of the cloud are in their infancy. You've seen people experimenting with the Amazon services, and I think with quite success. The smug word was just one example. There are other examples that they've done. Whether they really will be valuable for science remains to be seen. I mean, it's interesting to think how TeraGrid will evolve. You know, will that evolve to be part cloud and part supercomputer? I don't know. And so, yes, I mean, what you'll get from places like Amazon, Google, Microsoft are tailored cloud services on a platform. And we're developing a platform which you can be innovative on. Alternatively, there will be some people who want to build their own platform, right? And that they can do, but then they're not likely to have access to the sort of resources that these other companies will have. You know, when you're spending, you know, millions of dollars to build data centers around the world and put huge amounts of bandwidth to them. Not many people can do that. Right? So I think there will be different types of cloud, but the ones I'm talking about are these commercial services, and I hope we can make some available for science to play with, and that's one of the things that Dan Reed and Dennis Gannon, who's now joined us at Microsoft Research, are exploring to see if we can offer interesting cloud services for scientists. So we're trying.
Another question? Thank you.
So one of the emphases you had in your talk was interoperability of a whole bunch of things. And as we go into the cloud, or if we're running things on computers that are not our own, whether they're grids or clouds, there is the licensing issue. The one thing that I think characterizes a good part of the scientific community is that we don't write code in C or Fortran or variants much. We tend to use things like IDL and MATLAB much more extensively. And that's a big obstacle at this point in trying to move anything that I do, for example, into a cloud. So what do you think is the future?
No, I can certainly. When we were exploring grids with British Aerospace in the UK, they were very keen on grids because they have to collaborate with many sites and they did interesting things. But one of the things that they wanted to explore was they use lots of commercial software and they needed a different type of license to be able to run it on an indeterminate number of things for a short time. And of course their motivation was to save money. And of course the person who owned CFD code, Fluent or whatever it was, they don't want to lose their revenue. They want to get more money. And I think until it's proven that by actually having different, more flexible licensing, that you actually don't put the company out of business, you actually generate more revenue, I think there is a problem. And it'll be interesting to see how that evolves. But there will be people offering services, but whether MATLAB services will be priced differently or I don't know. But I think it's a real challenge for cloud and for grids, actually.
Anything else? Over here, please.
I was going to say I thought you'd been very patient, but okay. Yep. Carol.
So, Tony, you haven't really explored the notion of trust. So the reason scientists keep their data on a USB stick that they hang around their neck is because they don't trust anybody else with it, and they also don't trust that in 10 years' time that data uploaded to a commercial company will actually still be there. Now, of course, there is a false trust that they believe they can look after it themselves and the USB stick will still work and so on, but nonetheless, that's the perception. So what is what's your future vision for trust in the cloud?
No, I think that's absolutely right. I think not many scientists would be willing to entrust to a commercial operation unless there was a real service level agreement. But I mean, it's a little analogous to publishers, all right? You know, you publish a paper and then the publisher goes bust. There's no guarantee that they'll maintain their electronic things afterwards. And I think there are problems there. It may be a problem, you know, maybe that's a role. Well, let me take the UK example. I think the US is more complex. But in the UK, it may be that some of the research divisions that will actually take ownership of the data that they generate. They won't take ownership of all of it, but there's the British Atmospheric Data Centre and so on. And in the US, NASA and so on maintain and are commissioned to maintain data repositories. I think the university libraries can help, and also national institutions. So I was talking to the British Library last week, and one of the things that they're funded to be is to be around in 100 years. And so actually I think that organizations like that might show an interest, and they might be a sort of trusted intermediate third party. But I actually also tend to believe the LOX project in Stanford, lots of copies keep stuff safe, and that having multiple sites. So I think in the example I showed, yes, I think there will be people keeping things locally, and I think that's actually part of the role of a future university library. What the hell we don't go into the library to look for 1930s journals very often. they could get rid of those and turn the space into student housing or whatever, all right? Because they need to do a different thing, and their job should be looking after the intellectual output of the university, and I think they have a role. They also have a funding line. And if we weren't paying quite so much money for journals, which we can't afford, then they would have money to do elsewhere. But of course, there's different skills. So I think it's going to be a mixture, but I absolutely agree with you. I don't think scientists are ready to wholesale trust it to the cloud without some very specific guarantees. So I think we'll have to experiment, huh?
I'm going to give Tony the last word, but before doing so, final plea, evaluation sheets out at the front desk, lovely parting gift. Tony.
Thanks very much, Tom. Okay, so I just wanted to give some thanks for the workshop in Indiana, and first of all, I'd like to thank you for coming, because you actually are the ones who have the ideas and make the workshop worthwhile. So thanks to all of you. Some of you have come a long way. I'd also like to thank Geoffrey Fox, Anne Trefethen, and Dennis Gannon, who were organizing the IEEE event, and it was decided rather than have 2 workshops on eScience in North America, it would be sensible to try and combine them. Not all my team were enthusiastic about coming to Indiana in December, but I think it's been a good idea. I explained to them there were restaurants and bars, just like normal. So anyway, so thanks very much to the team, Geoffrey, Anne, and Dennis. Thanks also to the team in external research who supported the people you saw outside, Jennifer Carlson, Sarah Dangle, and Becky Culbert, who really worked hard to make things go well. And of course, the one person who deserves most thanks is Chris Toll, who, as the conference grew nearer and nearer, she grew more and more tense, and now she's obviously laid back and relaxed. So what I'd like to do, can you have a round of applause for all of those, but especially Chris? And thanks for coming. Thank you. So I'll see you at the unconference, which I don't really believe in.